Hi, I'm Rael Coping. Today we're going to be talking about seed oils, inflammation, and the anti-inflammatory diet. The diet which seeks to reduce the amount of inflammation in our systems, thereby increasing longevity, allowing us to live longer and healthier. What I'm hoping to do today is to take us through, from a novice level, people who are not too familiar with the whole matter, through a basic introduction to the concept, understanding a little bit of the biochemistry, a little bit about the physiology involved in the issues at hand. We're going to test the theories which put forward that omega-6 oils, seed oils, are pro-inflammatory, and then we're going to look at some current studies to see whether the fears are bearing out in reality. So we're going to go through it reasonably slowly, and we're going to try and get a deep understanding of all of the issues. By way of background, what we're talking about is, from an epidemiological perspective, society's made many advances in medicine, etc., and yet we still have this huge disease burden of heart disease, diabetes, and various kinds of cancer. And now, looking at it from afar, various researchers are saying, is it possible changes in our modern industrialized diet which are causing these diseases that we're talking about? And they've thrown a big focus onto seed oils as being potential creators of these various diseases. So I think the inflammatory effects possibly of seed oils are very topical, and it's a very technical issue. So we're going to go a little bit into the theory behind it, and it's very important to understand that life itself is an inflammatory process. So we've got going on in our bodies various reactions all the time which create reactive oxygen species. These are called redox reactions, and reactive oxygen species, we can think of them as sort of exhaust fumes or rust which accumulates inside the system. So inflammatory aging is a very generalized term which refers to the buildup of these redox metabolites, these reactive oxygen species, and these over time contribute to the aging of our systems related to various cardiovascular diseases, various cancers, and various neurological diseases. So that's inflammatory. It's a low grade, in the background, continuous buildup of reactive oxygen species. So chronic oxidative stress is low grade, sustained, and associated with inflammation. Now, inflammation itself is something which is characterized by an immune response. An immune response is when your immune system reacts to an antigen. It's a very rapid peaking response to a specific antigen, followed by a period of resolution. So actual inflammation and inflammaging are two different things. Just to quickly go over it, inflammaging, redox-driven oxidative stress, an accumulation of reactive oxygen species, and it's not a specific cause, it's just a low-grade chronic buildup of rust-type products, and they are treated primarily with antioxidants. There's also a component of looking at which kinds of foods might contribute to it more, but it's treated by antioxidants. An actual inflammatory response, though, is an immune-mediated inflammation. It's got a specific antigen, and it's going to be acute. You want to eliminate the trigger and look at a rapid resolution if possible. Now, we are in a murky space between inflammaging and classical inflammation when we're talking about the roles of fats and seeds as we are today. Now, the first thing to be aware of is little cells called M1 macrophages. Macrophages are part of the white cell family. They are sentinel cells. They normally reside in one tissue or another. If they're in the liver, they may be called Kupffer cells. But these M1 macrophages, specifically in fatty tissue, are very aggressive little cells. And one of the things that they do is they will amplify an inflammatory message which they receive to try and elicit a far, far greater response. So what it means is that if a person has got large body fat reserves, if they're overweight or obese, the probable biggest source of inflammation that they're going to experience is going to be derived from these M1 macrophages. So the first thing to look at, and I say that to anybody who wants to embark on an anti-inflammatory diet, the first thing to look at is how much body fat are you carrying, because excess body fat is likely to be a greater source of inflammation, and more important to reduce that than to cut at any specific inflammatory element of your diet. So that's on the one side, the physical element of body fat and its associated white cells. On the other side of it, we're going to be talking now specifically about two families of oils called omega-3 and omega-6, which themselves are very potent regulators of the inflammatory process. So where we reside today in this whole sort of continuum is on that brink between inflammaging and full-blown inflammatory response on both levels, the actual immune cells and the messaging effect of these fatty acids that we're talking about. That said, let's meet the players. So here we go. And I've chosen, I'm not going to say randomly, but it's not a comprehensive list. These are the oils we're going to be talking about. We've got olive oil, canola oil, peanut oil, corn oil, soybean oil, sunflower oil, and coconut oil. So quite a number of them, but I think it's a range of oils which we will be broadly familiar with, if not have them in our own kitchens right now. So the first of the fatty acids, which is the biochemical name for an oil, the first one we're going to look at is a saturated fat called lauric acid, which is the main oil of coconut oil. And looking at our bar graph there, it's quite clear immediately that coconut oil is far, far higher in saturated lauric acid than any of the other oils. Looking at the actual diagram, the illustration, what we can see with the fatty acid, the top has got a carboxyl end, the little blue and white oxygen elements at the top of the chain, then a long methylated chain, long carbon chain stacked together. Each of those carbon bonds is fully saturated either with a hydrogen or with a carbon. The biochemistry is not important. What's important, as you can see, it's a long, thin molecule, and because of that structure, they are able to pack very closely together in the membranes of our tissues, and that packing allows them to be solid at room temperature. So if we look at our pictures again, they have all the different oils. They all are liquid in bottles, but the last picture, the coconut oil, is actually a solid at room temperature. And if you've ever used coconut oil and kept it in the fridge, when you take it out of the fridge, it takes quite an aggressive amount of spooning to go and break that coconut oil down so that you can use it for whatever your purpose. So interesting, those saturated fats are solid at room temperature. Now coming back to our design of our little lauric acid diagram, we don't, in scientific nomenclature, we don't draw them with all the little carbons and things. The more typical way to represent it is just as a zigzag line between the different carbon atoms. Now the top end, with the oxygens, the carboxyl group, that is called the delta end, and you've got a long chain of carbon atoms. The bottom of the carbon end is called the omega end. Omega end. So delta at the top, omega at the bottom. Now we're going to introduce another fatty acid, oleic acid, which I'm sure you are familiar with from olive oil. And yes, look at olive oil, the first one. Look how high it is. The tall green bar, how high it is in oleic acid. Canola oil, very similar to olive oil. Coconut oil, the polar opposite. Coconut oil's got very high oleic acid levels. Now, you can see our little picture of the oleic acid, and the first thing we can see, it's not straight like the lauric acid. There is a kink in the tail, and that kink is caused by one bond which is not saturated. It is an unsaturated bond, and because of the nature of that bond, the tail becomes kinked and it can't pack closely together like the lauric acid could, and that necessary spacing of the fatty acids makes olive oil liquid at room temperature, as are all of the unsaturated fatty acids liquid at normal room temperature. Now, we are going to count the number of carbons from the omega end, and we've got there 1, 2, 3, 4, 5, 6, 7, 8, 9. So at the omega 9 position, there is one unsaturated carbon bond, so it's an omega-9 omega-9 monounsaturated. Easy. Okay, now we're going to meet some of our other players in the cast, and the next fatty acid that we meet is called linolenic acid. Linolenic acid, and you can see there's a little bit of it in canola oil, not too highly represented. The one seed oil high in linolenic acid is your flaxseed oil, which I haven't included in this graph. What is a seed oil? Basically any of these vegetable oils, with the exception of olive oil, is called a seed oil. I don't know why, but that's what it is. So now we're looking at this linolenic acid, and what we can immediately see is there are multiple of these kinks in the tail. Multiple unsaturated bonds, so it's a polyunsaturated. And if we do the same trick we did before and count from the omega end, we've got an omega-3, omega-6, and omega-9 level polyunsaturated. But we don't call it that, we just call it by the first position. So linolenic acid and omega-3 polyunsaturated. The last one we're going to look at over here is called linoleic acid. Linoleic acid, also a polyunsaturated, but in this case, the first unsaturated bond is at the omega-6 position. So linoleic acid is an omega-6 polyunsaturated. That's very important. Our bodies can make lauric acid, the saturated fat, which I think has got 16 units in it. The oleic acid, which is an omega-9, our bodies can make as well. Our bodies can insert that unsaturated bond at the omega-9 position. We cannot insert double bonds at the omega-3 or omega-6 positions. So that makes these fatty acids essential fatty acids. We have to get them from our diets, and especially so because they are so important in regulating our inflammatory response. So omega-3 and omega-6 fatty acids are essential, meaning they must come from our diet. Now, this is a great slide to present the idea behind the alarm being sounded around omega-6 fatty acids. Omega-6, the linoleic acid. Now, I think it's very cruel. The person who called the one linoleic and the other linolenic obviously had a sense of humor because the two sound so similar, but they've got such different effects in the body. So the linolenic, I put a little picture of Nick Cage there, omega-3, so that we know omega-3 is Nick, for Nick Cage, linolenic acid. Now, we're looking at the blue one right now, the linoleic acid, and the alarm has been sounded because various smart people have said, look at the volume, look at those blue columns, how much linoleic acid and omega-6 acid, which is associated with pro-inflammatory, causing inflammation, look how much of it is entering our food chain. And we never previously had these huge amounts of peanut oil, corn oil, soya oil, sunflower oil. These are reasonably modern additions to our diet, and they're saying this must be impacting on the level of inflammation in our systems. Let's take it a next step further and check out the magnitude. Is this actually something of substance? So we've got here on your left-hand side the United Nations Food and Agricultural Organization graphs of oil production. So this isn't a survey based on asking people what have you been eating. People can never remember. This is what amount of oils have been produced globally and are entering our food chain. So we can see at the bottom olive oil, groundnut, that's peanut oil, coconut oil. They are minor contributors to the global oil production. The biggest vegetable oil components are the sunflower oil, those blue graphs, but the yellow, that soybean oil, is a major contributor to the amount of seed oils being produced globally, and obviously that's entering our food chain. So what I've done in that next little graph is I've just split out the actual fatty acid species as represented in this graph. It's not There's obviously other oils which come into it as well, but it's good enough for us. And what we can see at the bottom, the red line, the linolenic, the omega-3, the anti-inflammatory oil, is quite a low contributor to that volume of oil coming in. The blue linoleic acid is a massive contributor. And according to this graph, my estimate is that between 2010 and 2022, the amount of linoleic acid entering the global food chain has gone from 40 million tons up to 60 million tons. So are these various researchers validated in sounding an alarm? Yeah, I think they have got a very good point. Now, the second question is, outside of just the pure oils that we may be consuming, are these oils also entering our food chain, the production of our other foods as well? Now, some smart people have gone back and looked at the primordial times, the hunter-gatherer societies, etc., and they've said, what is the primordial ratio of omega-3 to omega-6 in our historical primordial diets? And what they've said is it's roughly a 1-to-1 omega-6 to omega-3 ratio, perhaps 2-to-1. They're hypothesizing that up to a 5-to-1 ratio of omega-3 to omega-6 is still fine. Back in 1985, they're saying that ratio was up to about 10-to-1. And in our current food production environment, in most societies, it's 20-to-1. In other words, it's 20 times more of the blue omega-6 oils entering the diet than the omega-3, and in some societies, in the Asian societies, as much as 50-to-1. Now, we're looking by proxy at egg yolk, and we're comparing here some American studies, and the free-range egg has got that roughly 1-to-1 ratio, omega-6 to omega-3. American store-bought eggs, that ratio in the yolk is 20-to-1 omega-6 to omega-3. Chickens that are fed on fish meal, the ratio goes down from 6-to-1, and chickens fed on flax seeds are back to those primordial ratios of 1-to-1. So not only the amount of processed oils that we're consuming, but also the amount of these oils and or grains which are being used as feedstock also impact on the amounts and ratios of these oils entering our diet. Very interesting. So now, what is the concern? We've heard these words, omega-3, omega-6. Why? Why are we even looking at them? And let's take a look here. So bear with me a little bit, those who haven't done biochemistry before. The top of this drawing is my rendition of a phospholipid bilayer, which is basically a cell membrane. It's a fatty acid with a little phosphate on the one end, and these phosphates are polar, whereas the chain of the fat is non-polar. We're not going to dwell on that too much. It forms a nice little waterproof barrier, which our cells then use as membranes, right? Now, the polyunsaturated fats, all of the fats making up that bilayer, the membrane, are basically represented in the ratios in which they are in our diet. So what we eat, the body chops up and sticks into these membranes. So our membranes are made up basically of the prevailing oils in our diet. This picture here is showing a little scissors, a little phospholipase enzyme, which is cleaving a phospholipid inside the membrane, and it's releasing, taking off the phosphate and releasing that fatty acid into the cytoplasm, into the body of the cell. And now that fatty acid, which it's cleaved off, is arachidonic acid, a new word, arachidonic acid. And as it cleaves off that arachidonic acid, what happens? Boom, we go straight into second year biochemistry. And don't be discouraged by this schematic, by this diagram. We're not going to dig into it too much. But what's very important is to understand that this arachidonic acid is a potent initiator of the inflammatory response that can go via the cyclooxygenase pathway, the COX pathway, which then causes us pain, trembles, water, swelling, puffiness. On the far side, the lipoxygenase, the LOX pathway. If you've got an asthma, a respiratory condition, it can cause a constriction of the bronchi, difficulty breathing, cytochrome P450, all sorts of inflammatory processes can be set off. Difficult sometimes to relate to because we're talking about oils, but I think it's easier to relate to if we understand the medications that in fact block those pathways. So prednisone, if you present to your doctor with all sorts of inflammatory things going on and it's out of control, what does the doctor do? Give you a cortisone, a prednisone, and that basically switches off that phospholipase enzyme and takes the arachidonic acid out of the system, shuts the whole inflammatory process down. Cortisone, very powerful because arachidonic acid is very powerful. We're going a little bit further down this flow chart here. Aspirin, ibuprofen, coxflam, these are medications that blocks your COX pathway, your cyclooxygenase pathway. So we all know if you've had terrible stiffness, if you've had an operation, the pain that you get from that, and the ibuprofen, the non-steroidal anti-inflammatories, are going to block that pain. Very powerful. And on the other side, we've got your Zyflow for your asthma. So, I mean, I don't have asthma, but I can imagine when you have that restriction. So why put in these medications? Because sometimes in the food space, it's difficult to imagine. We imagine foods as quite inert things, but these fatty acids have got very powerful consequences if they trigger inflammation inappropriately. And I think it's easier to understand that in terms of the medications that are their counter. So now, another busy graph here, another busy illustration. And what we've got is your omega-3 and omega-6 pathways. Now, bear with me. We've spoken about your linoleic, omega-6, the blue one, and linolenic, the Nicolas Cage, the omega-3, the anti-inflammatory. But when I've illustrated to you now the inflammatory response, I'm talking about arachidonic acid. What's the connection? Well, let's take a look here, and we will see that here your linoleic acid is your major dietary source of your omega-6. It takes 2 steps, a desaturase and an elongase step, to convert it to the pro-inflammatory arachidonic acid. We haven't talked about it, but the omega-3 has got an opposite effect. Your linolenic acid gets converted to EPA, eicosapentaenoic acid, or DHA, docosahexaenoic acid. I do know what it is. Docosahexaenoic acid. I'm going to say it again. Omega-3 has got an equal but perhaps opposite effect in reducing inflammation, and there the active compounds are EPA, eicosapentaenoic acid, and DHA, docosahexaenoic acid. So again, our linolenic acid needs to go through a number of desaturase and elongase steps to get to be those powerful antioxidant fatty acids. The issue is that the desaturase and elongase enzymes for both of those processes are common to the two groups. The two groups are competing for those pathways. And it's been thought until recently that it's just a competitive inhibition. In other words, those little desaturase enzymes are going to work on fatty acids in the magnitude that they present. So if 20 times more pro-inflammatory omega-6 presents than the omega-3, you're going to get 20 times more inflammation. This is the big battle going on between the two of them. They have got very different functions, but they are fighting for access to the same desaturase and elongase enzymes. Now, important. These desaturase enzymes have got multiple polymorphisms. What does that mean? A polymorphism is when an enzyme can exist in slightly different forms among different people. So they will all function a little bit differently, not to the point that the person won't be able to survive, but different enough that they might have different outcomes when they're presented with those same oils. So the first thing that we know, this is not going to be a one-size-fits-all situation. Different people will respond differently to different omega-6 seed oils, and we've always got to bear that in mind. It's not a one-size-fits-all situation. Secondly, these desaturase enzymes have got multiple roles, especially under energy restriction conditions. They've got other things to do other than just desaturate these fatty acids. And they've got multiple regulators. It's not just this, they will process whatever's presented to them. It's far, far more complex than that. So very interesting to bear in mind. Now, what is this trout doing in the middle of the diagram? We've all heard of omega-3 fish oils, and we've said that your omega-3 and omega-6 oils are essential. Now, although these flow charts are showing us how the dietary sources are going to be converted to the more active species in the inflammatory process, it's not such an easy thing to do. It takes a fair bit of time, a fair bit of effort. Some of the processes are sent off to the liver and sent back again. So under normal conditions, our bodies can produce plenty of these downstream inflammatory mediators, but under inflammatory conditions, or when the system is being pushed hard, they are what's called conditionally essential. So generally it's fine not to be eating in the diet, but if you are suffering from inflammation, your body may not be able to produce enough of these anti-inflammatory omega-3s, under which conditions, yes, it becomes essential in its own right. So if we can consume that EPA and DHA in its final form, that takes a big load out of the system, and I think it's very well researched that what we call omega-3 fish oils have got multiple benefits across the spectrum. I'm not going to dive into that now. The fish itself is not making the omega-3 EPA and DHA. It's eating krill, which in turn have eaten phytoplankton and things which have made it themselves. So it's not big animals that make it. It is bugs, cockroaches, phytoplankton that make it. So we've talked on the one side, chickens, which through no fault of their own are big sources of omega-6 because they're being fed generally on corn. On the other side, we've got the salmon, oily fish, often high in omega-3 oils. Cockroaches, not many of us are going to eat. And the cows, the grass-fed cows, are ruminating, and they've got a lot of bugs inside them which are producing these omega-3 oils. Now, there's a little note there, nutrigenomics. So if we take that salmon from Canada, where it's living close to the Arctic Circle there, and eating krill, and that krill has eaten little phytoplankton or phytobacteria that are living in the freezing cold Arctic water, that will be high in omega-3 oils. Why so? Why will those little bugs make that very complicated, very laborious omega-3 polyunsaturated? We think it's mostly as an antifreeze. So in cold conditions, these bugs and phytoplankton and things are going to produce omega-3. Now you can take that same salmon and that same phytoplankton and that same krill and put it in Durban Harbour where the water is warm, and it's probably not going to produce that same amount of antifreeze. Same with the beef. If a cow is being fed somewhere along the garden route where grass is plentiful and lush, and it's going to be ruminating on fresh grass and bugs, probably produce a lot of omega-3. If we take that same cow here in Cape Town, which is a far more arid area and probably going to be grain-fed, it's not going to produce those same omega-3 fatty acids. So just something to consider. Now this graph, diagram, illustration is very confusing, deliberately so. This is the issue that we're dealing with. It's not a cut and dried situation. It's not a one-size-fits-all situation. We're just highlighting some of these issues which are going to make it a highly environmentally dependent issue, individually dependent issue, and various other factors are going to come into it as well. So, yes, that's what it is. In summary, though, the omega-6 is typically anti-inflammatory. In summary, though, the omega-6 is typically pro-inflammatory, causes platelet aggregation, and causes vasoconstriction. The omega-3 generally anti-inflammatory generally reduces platelet aggregation, generally is vasodilatory. And of course, we know the omega-3 and omega-6 fatty acids are competitively metabolized in two distinct pathways, but they are competing for a common enzyme system. So now, that is the theory. Let's see if this actually bears out in reality. And we're just going back now into our paradigm of inflammaging versus actual inflammatory response. And it's just important to note that in inflammation, there are various very well-known inflammatory markers which are very commonly tested in studies, etc., and we can get quite easy access to them. In terms of inflammaging, the redox oxidative type environment, there's no single metric, there's no single measure of what is going on there, and many of these studies will have very novel molecules that they're monitoring, etc. And I'm just looking here at this specific one. There's an oxidative LDL. We're not looking at that now, but this next study that we're going to look at is looking at oxidative byproducts. So it's kind of traversing those two. Very nice study, and we can talk perhaps about the macrophages as well. So what did these guys do? So obviously in preparing this talk, I've read very broadly, but a lot of these review articles and things are very dry, just quoting statistics. So I think it's actually nice. I've chosen several illustrative studies which I think we can relate to and make it a little bit more human and relatable, right? So this study, what have they done? They've taken the normal diet, as we've just seen, high in the linoleic acid, the blue bar in the bar graph that we talked about, and then actually affect the way that they're metabolized. So they're talking here, the linoleic acid, we've met it before, and downstream of that, they're talking about various byproducts, oxidative linoleic acid metabolites. They call it oxalams. Now these things are related to Alzheimer's disease, heart disease, etc. So now they can be produced either through those pathways that we saw, the COX pathway or the LOX pathway, or even if they're not metabolized actively, just through oxidative reactions, they can also be broken down and appear in the cytoplasm. So what does it say? In the theory is just having them in the tissue, they will be metabolized, they will be potentially pro-inflammatory down the line. Now, why I like the study, they've taken people with a normal linoleic acid-rich diet and they have counseled them in how to reduce that linoleic acid level. So people in the study were given food, about 80% of the diet, but they were also given instruction how to reduce their own linoleic acid exposure. And then they were monitored at the start of the process and after 12 weeks to see what the intervention was. Now, in addition to that, they also addressed this question of the omega-3 to omega-6 ratio. We talked about that a few minutes ago. So let's see what do they find in their study. And just a quick word on statistics. A p-value is a probability value which tells us whether something is a significant finding or not. And a p of 0.05 is generally considered a threshold of significance. A lower number is more significant, right? So the lower the p-value, the more significant it is. So we're having a look here at this table of their findings, and we can see at the start of the study, these people had a linoleic acid presence of about 6.7% of their dietary intake, the percentage of the energy, and after their intervention, that dropped down to about a third of that, 2.42. So through the intervention, yes, they were able to dramatically, significantly reduce the amount of omega-6 in their diet. Now, we've got the table of all of the oxalams that they have been assessing over this period. We're certainly not going to dive into that, but look at these p-values across the board. Minute p-values, meaning it's a highly significant reduction in all of these potentially pro-inflammatory and disease-causing oxalams being produced. Very, very interesting. Now, let's look at this question of the addition of the omega-3. Same story. They gave them instruction how to do it, what supplements to take, etc., and they left the people apply it of their own accord. So I think it's very reflective of the kind of environment that we're in now. Give people information, let them get on with it and do their things, and the kind of results we see, or that might not be perfectly controlled environment, it's kind of a realistic sort of expectation. So now we're looking at these graphs, and the white box plots are the start of the study, and the colored box plot with the pink or the red or the orange are at the end of the study. And we can see across the board that the 12-week measures are lower than at the beginning. But if we look at the p-values, these are far from significant, right? So it's not statistically significant at all, this addition of the omega-3 oils to these people's diets. But remember, this is over a 12-week period. So if we talk about over the extent of their lifespans, is the reduction in oxalams going to be significant? Probably yes. It probably is going to be interesting. An interesting slide to take a look at. Now, we talked also about the space where activation of macrophages, the M1 macrophages, etc., would be a critical element in the whole picture. And we said if you're carrying a lot of fatty tissue, this is probably going to be a more likely source of inflammation than anything else. So this is a study where they've taken, this is an in vitro test tube type study, where they've taken macrophages and they have exposed them to different species of fatty acid. And they've seen, does this change the way in which these macrophages are responding? And the answer is yes. Now you'll see there's 3 different categories of response that they put on this table. They said an increase in inflammatory response, a decrease in inflammatory response, and conflicting results in the inflammatory response. And I'll tell you, having read this in detail, the vast majority of this paper is conflicting, confusing, and indicative of a very, very complex regulation of this environment. So they've summarized it down to this graph. I didn't, and I could never. So we're going to go with their finding. But from my side, and you're welcome, please go read it yourself, it just shows how complex the fatty acid regulation of macrophages is. Is there something going on there? Absolutely. What is going on? Unclear. But what they've said is the omega-3s, that's the linolenic, is generally going to reduce inflammation. Saturated fats, and I think they're talking here predominantly like from meats, from steak and stuff like that, generally going to increase inflammation. Interesting, omega-6 generally decrease the inflammatory response of macrophages specifically. So I'm just going to pause and get a little bit out of our current paradigm and talk a little bit about macrophages. So I've mentioned that they are sentinel white cells typically resident in a tissue, and should that tissue be subject to invasion by some kind of a pathogen, they will attack this thing. Very, very functional, aggressive cells. If they can't cope with the environment, they will send out chemokines and they will attract more help from things called monocytes. And when these monocytes enter this infected tissue, they will differentiate into macrophages themselves. And they may go either into that M1 macrophage form that we've talked about now, or they may go to form an M2 macrophage, which is kind of the opposite of an M1 macrophage. So M2 are anti-inflammatory. They do a lot of mopping up operations. They pick up pieces of cells which may become pro-inflammatory, etc. Right? So why I've put it over here, and it's a little bit outside of what we're talking about, is because it's generally thought, and we're not going to go into it in detail now, that this prevailing cytokine environment, which tells the monocyte whether it's going to become the aggressive M1 or the healing M2 macrophage, is largely influenced by omega-6 fatty acids. So it's outside of the inflammatory messaging, but it seems to be an effect that some are saying the omega-6 has on producing M2 macrophages. It's important. We're not going to delve into it, but let's just park it there for now. So that is the environment. Are these seed oils entering our diet? Yes. Are they changing our food system? Yes. Does our body respond to them by increasing inflammation? Yes. Does it affect our immune system? Yes. but what is the overall impact if we look at broader studies of inflammation? Now, these studies coming forward are not on your inflammaging, for whatever reasons, they are on full-blown inflammation, right? So let's take a look at them. And the first one we've got here is based on a Framingham study cohort, which is a very, very respected study, started, I think, in the 50s on heart health, and they've gone back and they've drilled into this information and found various things. They're looking now at the red blood cell linoleic acid. So red blood cells, you know what a red blood cell is? It doesn't have a nucleus, so it can't do very much. Once it's formed, that's it. It's formed, and they're looking at the membrane, how much linoleic, the blue pro-inflammatory, or so we've said, fatty acid is in it, and they're saying, well, we've got all of these markers from the Framingham study. Is there a relationship between those linoleic acids in the membrane of the red blood cell and other inflammatory markers that we're finding? And why did they do it? Because they've said here, researchers have advocated both for and against reducing the dietary intake of omega-6 oils, and we've said what they're doing there, and they're looking at full-blown inflammatory markers. They're looking at the side of the spectrum, right? What's going to cause that increase in inflammation? And what do they find here? I'm going to just highlight here, observed a weak but statistically significant inverse association between several types of inflammatory biomarkers with red blood cell, omega-6 polyunsaturated fatty acids. This is the point. Our findings do not support the hypothesis that omega-6 fatty acids are pro-inflammatory. Interesting. Let's look at the next one. Diabetes. Also, big study, 16,000 people there. They're looking at all sorts of statistics here. And what they're finding, that the omega-3 polyunsaturated fats and alpha-linoleic acid are inversely associated with type 2 diabetes. Here, the EPA and the DHA are not significantly associated. And linoleic acid, inversely related. Arachidonic acid, not significantly related. So, again, what we're seeing here, and I think this is the key thing we're talking about here, that your omega-6 is inversely related. In other words, higher omega-6 fatty acid levels are not showing up as pro-inflammatory in the diabetics. It's showing as a reduction in the inflammatory risk of diabetes. Another summary, a review of linoleic acid consumption with cardiovascular risk factors. What are they? Your total cholesterol, your LDL, your HDL, triglycerides, etc. And what do they find? A general reduction in total cholesterol, a reduction in LDL, that's the bad cholesterol, reduction in VLDL, reduction in HDL, that's the good one, and variable responses for the triglycerides. They're saying there's no optimum dose known for how much omega-6 you should be taking in, and they don't recommend more than 10%. It's a conservative kind of a finding. So isn't that interesting? So all of these studies, and I'm not cherry picking here, I've just taken some with some level of interest for illustration. They are almost across the board saying that yes, there is a relationship between your omega-6 and your various markers of inflammation and or risk, and they all are showing a inverse. In other words, the more omega-6 oils you've got, the lower the markers of inflammation and or risk. So quite the contrary to the theory that we've seen presented. And another thing we're looking at, just for kicks, this is a dietary inflammatory index. So this is a very blunt instrument. I don't want to give it too much kind of weighting in terms of how we interpret it. But what these guys have done, they've taken large-scale food frequency questionnaires. You know, when you get the census coming around and you've got to fill in what you ate for the last year, we all know you don't fill that in with too much attention. But they've taken populations where there've also been blood work measurements done on them as well. And now they're looking at those questionnaires and seeing, does that in fact bear out any relevance in the blood works done? So a blunt instrument, but let's look what it says. Now, the first thing we're going to look at, the macronutrients. Those are the nutrients that can provide us with energy. Fiber, massively anti-inflammatory. Does that mean fiber is anti-inflammatory? No, it means people eating high fiber diets, which might be, generally speaking, they're eating more whole foods, they're cooking their own food, they're going to take in less processed foods. It might be a certain type of person who focuses on that. They may have various other psychographic and sociographic characteristics which are driving the low inflammation. So we can't say it's causality. An association is not a causality, but nonetheless, very interesting. People eating a lot of fiber tend to have lower levels of inflammation. Let's talk about the things we've actually mentioned today. The saturated fat, yes, it seems to create more inflammation. And here they'll be talking, not coconut oil, here they're talking more about animal fats. Total fat, generally anti-inflammatory. Omega-3, let's start with the monounsaturated, the olive oil, yes, associated with anti-inflammatory. I think we were expecting that. The omega-3, yes, anti-inflammatory. Omega-6, anti-inflammatory. So it's just being borne out as well by this study, which carries on. We'll do that. We'll do more of the study in another talk. So just a little bit of a caveat, because I think we've seen quite clearly the magnitude, the theory, why we think that it could be a problem, and the reality that it's not really bearing out in reality the way that the theory proposed it. I'm going to put in two little points of interest. Firstly, we talked about the omega-3 oils, and generally speaking, krill oil is thought to be superior to your normal omega-3 fish oil. It's also a lot more costly. But why is it thought to be superior? Because krill oil is already in that phospholipid form that the oil is incorporated into the membrane. Your omega-3 fish oil is a triglyceride. So the body still has to chop it off. If you've done biochemistry, you'll understand the triglyceride goes to the liver, it's got to be processed, come back to the cell, and converted to a phospholipid, etc. So it's a far more involved process, taking an omega-3 fish oil and getting it into the phospholipid form that's wanted, compared to your already phospholipid krill oil. Now, the second thing, which I think we have to mention, I know specifically for canola oil, but generally speaking, as these results are coming out, the anti-seed oil crowd, I don't know what to call it, I don't want to be divisive about it, the focus kind of shifts not so much on the properties of the omega-6 oil itself, but onto the production of that oil, onto the hexane level. Hexane is a solvent, so they will often use hexane. Once they've mashed the seeds down, they'll use the hexane to extract the oils, and hexane itself can be toxic. It's not a great thing. They're busy reviewing it. Both the FDA and the European food safety people are busy reviewing it. But I'm in Cape Town, and I think many of you people will be. Now, most of our canola and other seed oils in Cape Town are not produced using hexanes. Our oils are produced in a cold-pressed method, so it's actually quite a bespoke method. So something to bear in mind. If you are entering this seed oil debate and being scared off by hexanes in North America and Europe and Asia, yes, it is something to think about. But here in South Africa, our locally produced etc. are cold-pressed oils, no hexanes. So guys, that was quite lengthy, and it might be broken down into different sections, but I think that's a nice overview of the background and the current status of the controversy around omega-3 seed oils. I'm hoping going forward to bring in various experts to come and talk with me around these very, very interesting and specialized topics going forward. And I'm going to say I did not, in preparation for this talk, read any of the contemporary popular books on the matter. So if I've skipped over certain issues, or if you have got a specific interest, perhaps a medical person or an enthusiast in the section, please drop me some questions, drop me some comments. I'll be very, very keen to hear from you and hopefully to respond appropriately. So thank you very much for this. I hope you've enjoyed it. It's been a lot, but I think it's been well worth it. Thank you very much. I'm rail coping.